when I was about 10 years old. I found a book in the public library which talked about this problem, and like many other mathematicians, that's one of the things that got me excited about mathematics. Obviously, as a 10-year-old, I didn't do very much on this problem. I kept trying in my teenage years, and then I abandoned it when I was a student. This problem has a long history. It was tried by many mathematicians in the 19th century, but most mathematicians seem to have given up in the 20th century. Until about 8 years ago, there was a big breakthrough, and someone related Fermat's last theorem, or this is the problem I've been working on, with another well-known problem in number theory. And from that moment, when that link was made, I've worked on it. So it's about 7 years now. I didn't start with any idea on how to solve this problem, so that was a problem, and it took me 5 years to get the first real breakthrough, and then I finished it probably about 3 or 4 weeks ago. There are lots more problems in mathematics. There are many unsolved problems. I think I'll wait until I've written this solution in a way that satisfies all the experts, and then I'll start thinking about my next project. The main significance of this problem is symbolic. One doesn't expect any real applications of this kind of result, but one never knows. Primarily it's symbolic because so many mathematicians have tried it. It's led to the creation of so much mathematics itself that everyone has thought of it as the dream of mathematics to solve such a problem.
Welcome to tonight's special program on Fermat's last theorem. And I see a few seats and a few people coming in, so please feel free to take a seat while I make a couple of introductory remarks. I'm Will Hurst, the publisher of the San Francisco Examiner, and I'm going to be the moderator for tonight's session and introduce some of the speakers. On June 23rd of 1993, something extremely exciting in the mathematical world happened. Some of us were reading the New York Times innocently that day. Others heard about it via email or maybe a day later. And that was the announcement that a mathematician named Andrew Wiles had proved something that mathematicians had been trying to prove for 350 years. He had finally resolved Fermat's last theorem in the affirmative. Now, tonight's presentation is really aimed for a general audience. And so we expect that we may have some students in the audience, professionals from other allied fields, perhaps some professional mathematicians as well, and members of the general public that are interested to find out why the fuss about this theorem, what's exciting, how did Andrew Wiles do it, what does it mean? And we're going to try and get at some of those questions, and we have some very talented and brilliant speakers who have condensed a lot of complicated mathematics into some simple talks of about 10 minutes each. I don't think anybody should be worried if they miss a detail here or there. Even professional mathematicians go to talks and miss a detail here and there. But try and get a hold of the general concepts, feel the flow of it, and we're going to have some questions at the end, and don't worry, there will not be a quiz. Thanks ought to go to the Mathematical Sciences Research Institute, who is our primary host this evening. MSRI, as it's known, is a research institution, a little bit like the Princeton Institute for Advanced Study, located over in the Berkeley Hills. They have a Zen monastery-like building overlooking the Bay Area, and a lot of interesting people come through there, mathematical researchers who give talks, listen to other people's talks, and talk to each other. Bill Thurston, who is the director of MSRI, set out a goal for the institution to do some outreach. This was before the announcement of the proof of Fermat's last theorem, and so this program tonight is an effort to try and have MSRI be the agent for public awareness of mathematics, and we hope you'll enjoy the program. I guess I should also answer the question, why am I here? Why is Will Hurst here? And I can only offer two answers. One is that about 25 years ago, I was a college student in mathematics. And I had a high school teacher who told me, look, all these things that you learn in elementary school, arithmetic, fractions, geometry, algebra, all of these things are the preparation for you to find out what mathematics really is. And although I didn't go on in the field, I think sometime in my college education it dawned on me that there was a whole world of mathematics beyond the elementary, a world of beauty and logic and a kind of adventure. And hopefully the speakers tonight will convey that for you in ways that I could not. And I guess my second reason for being here as a publisher, I believe in public outreach and in providing information to the widest public about not only news, but also ideas. Tonight's speakers are the real experts, and they will tell us a little bit about the history, the prehistory of Fermat's last theorem and the part between Fermat making his conjecture and its proof, and they will take you through some of the important ideas that are within this proof. And they will try to answer the question, why is this important? What does it connect to, if anything, in ordinary life? And along the way, what is math culture like? What do mathematicians do? Why do they do it? What excites them? So before we begin, I've been asked, and this is the hard part for me, to sort of remind the audience, what exactly does Fermat's last theorem say? And perhaps the easiest way to try and illustrate this theorem, and it has a very simple statement, it's the proof which is hard, is to recall something from high school algebra and geometry, Pythagorean theorem. And perhaps you have come across or recall the 3, 4, 5 triangle. This is a right triangle with 3 sides. Most triangles have 3 sides. It has this side next to the right angle and this side, and then it has this hypotenuse. And Pythagoras noticed, and in fact the ancient Babylonians noticed, that if you took the length of this side and squared it, the length of this side and squared it, added those two together, you got the length of this side squared. And the 3, 4, 5 triangle illustrates this because 3 squared is 9, 4 squared is 16, the sum of 9 and 16 is 25, and that's 5 squared. Now the interesting problem, the problem that makes this a number theory problem, is that these are whole numbers. These aren't just sort of arbitrary dimensions. And the ancients understood that you had a 3, 4, 5 triangle and a 5, 12, 13 triangle, and in fact you have an infinite number of triangles with integer sides, whole number sides, that stand in this relationship of a square plus a square is equal to another square. What Fermat noticed was that you could not do this if instead of squares you tried it with cubes or with fourth powers. And a cube is something times itself again. X times x times x. And he conjectured, he thought in fact he had a proof, that it was impossible, except in this case of squares. And what this theorem says is that no matter where you look, no matter how big the numbers you search for, you will not find a triple that stands in this relationship. Not for cubes, not for fourth powers, not for any power except 2. people have been trying for 350 years to give a mathematical proof that there are no other solutions except the ones we've talked about. Now that's the easy part. That's the statement of the theorem. Now comes the fun and the interesting part. How do we know it's true? And we only found out it was true on June 23rd, so it's a relatively new piece of knowledge. To begin, our first speaker is Robert Osserman. And Bob Osserman is the deputy director, one of two, of MSRI, a professor of mathematics at Stanford University. His research interests are in the direction of geometry. And Professor Osserman is going to talk about the Pythagorean theorem, the kind of prehistory of Fermat. Bob?
As you heard, what I will be talking about was basically the equation a squared plus b squared equals c squared, the original case that led Fermat to the thought, what about if you go to a cubed plus b cubed equals c cubed and fourth powers and so on ad infinitum. And the later speakers will start from the third power and tell you what happens the rest of the way, but I will just stick to the original equation. Well, what I really will do is start out with a very practical problem, which I think many of you may have faced at one or another time, and tell you about how one can find a solution. And the problem is simply this. Suppose you have a choice. You want to decide which is a better deal. Would you like one large pizza or a small plus a medium? Now, as usual, we'll make life simple, and let's simply assume that the price comes out the same. You charge the same amount for the small and medium as they do for the large. What we really want to know, which one gives us more pizza? Well, this is a very old problem. The Greeks thought about that too. And some 2,000 years ago, they came up with a method of solving it, which I'll let you know, so the next time you face the problem, you can do it. You bring your pizza knife, and you simply cut each of them in half right down the middle, like that, and then put it out there. Cut the medium, and place that next to it, and finally, you cut the large. And place all three of them with the straight sides together so they form a triangle. And then the trick is this. You look at the angle that's opposite the large pizza. That's this one down here. And you check, is it bigger or smaller than a right angle? Now in this case, it's smaller than a right angle, and that means you're better off taking the small and the medium. On the other hand, had you had a pizza and you did this and it was an extra large, there the angle is bigger than a right angle, and in that case you want the large one rather than the small and the medium. Now there's just one case which is right in the middle where you carry out this process, and lo and behold, what you get is a right angle here opposite the large side, and that leads you to what we call the Pythagorean theorem. And as you all undoubtedly learned in school, what the Pythagorean theorem says is that the pizza on the hypotenuse is the sum of the pizzas on the two sides. Now, you may have learned it with other words. Often they use no words at all. They just use this formula, a squared plus b squared equals c squared, which in fact simply refers to the fact that the a squared, if the sides a and b are the sides, the two small sides, c is the hypotenuse, then what this tells you is that the sum of the squares of the two sides is equal to the square of the hypotenuse. Now, of course, when you're talking about pizzas, then you want to put a pi in there, and so sorry about that. You all know that that the area of a circle is pi r squared. So if you're faced with a 6-inch pizza, an 8-inch pizza, and a 10-inch pizza, then you see the 10-inch pizza would have a radius of 5. Pi times 5 squared would be the whole pizza, and you put a half, and that's what you have on your hypotenuse. You do the same on the two sides, and you have to check, is it or isn't it true that the one on the hypotenuse adds up. You write down the equation, and it ends up being 3 squared plus 4 squared is 5 squared. And as Will mentioned earlier, this is a correct equation. It's an example of the Pythagorean theorem. I wanted to mention one special case which arises and turns out to be particularly interesting. That's where it turns out you have two small pizzas of the same size, so that you get what's called an isosceles right triangle, perhaps, where these are equal. Hypotenuse is C. If you do the Pythagorean theorem, you'll find that the ratio of the length of the hypotenuse to the side is just the square root of 2. Now, the square root of 2 is a very interesting number. You can prove that it's what's called an irrational number. It is not the ratio of two integers, two whole numbers. It is not a fraction. So if you try to make such a triangle with whole numbers, you'll never get a right angle here. So that was an interesting fact that the Greeks discovered also. I think that's as much as I want to say about the Pythagorean theorem, but I did want to say a little bit more about Pythagoras and other things that he did. Pythagoras founded a philosophy or a religion, whatever you want to call it, a cult sometimes, the Pythagorean Brotherhood, of which a basic tenet was that nature, which often seems totally irrational and unpredictable at the whims of these gods that are full of human frailties, in fact, when you look closer, has numerical and mathematical underpinnings. And you can often find mathematical reasons for explaining things which on the surface you wouldn't understand at all. And one of the examples that was given most strikingly was that of music. People had noticed that if you take say a string and tighten it and pluck it, you get a certain note. And if you divide it in different ways, sometimes the notes you get will sound very consonant or harmonious, and sometimes they'll sound discordant. And this is a kind of an aesthetic judgment or an emotional reaction, and yet what they discovered, there was a simple mathematical reason. And to illustrate that, I'd like to show you an instrument which is a rather simple one known as the monochord. Looks like this. You have one string, but you're able to divide it with a kind of movable fret here, so that the ratio of the two sides can be divided any way that you like. Now, I've just put it here where there's a marker, and if it's marked right, it's divided so that the ratio of the length of the two sides is 4:3. That's a simple numerical ratio. If the Pythagorean theory is right, then that should give you two consonant-sounding notes. So let's try. That's one side. That's the other. And indeed, that is an interval which we're familiar with, which is called a fourth in modern notation. But at any rate, it's a consonant sound between those two. Now, if you move a little bit so that the ratio is not simple numerical, then it should probably not be so nice sounding. Let's try. That's the kind of thing you'll get in general when you don't have a simple interval. Now, if we move it up further so that you get, now it's divided 3:2. So again, one would hope for something simple. And again, you have a consonant sound, harmonious. That's actually the interval we call a musical fifth with a ratio of 3:2. So what I wanted to do was simply ask the question, what happens when you combine the Pythagorean theory of music with a Pythagorean theorem about right triangles? And of course, you can guess what you get is a musical triangle. Now, that's not exactly the kind I was referring to, but in fact, what would I mean by a musical triangle? I would mean a right triangle where the sides have lengths that are in simple ratios, so that if you constructed such a triangle, it would make nice harmonious sounds. And in fact, I believe there may be one in the wings. Here comes one. Here are two musical triangles. I would like to thank the Exploratorium shop for this as well as all the other great contributions. Now, first of all, let's look at this triangle. This one, you notice, has two equal sides. It's an example of what we called an isosceles right triangle. And so there's a string simply wrapped around with pulleys to make sure that the tension is the same on all three sides. So if we try these two sides, you get what's called unison. It's the same note because of the same length. On the other hand, if you try these two sides, now I have one side and the hypotenuse. What do we get? That's the interval that you get when the ratio of the lengths is the square root of 2 to 1. You remember I said when you have two sides equal, then the ratio of these lengths is irrational. Not only is it not a simple numerical ratio of 3 to 4 or 5 to 3, it is not the ratio of any two whole numbers, so it should be kind of maximally discordant. Well, that particular chord, you might be interested to know, ever since the Middle Ages, was considered the most dissonant that there was. It was known as the diabolus in musica, the devil in music, and you were told to avoid that at all costs. On the other hand, we can look for a triangle where we have simple ratio of sides, and again, in this one, this is the one that we've mentioned several times. The sides are length 3, 4, and 5, so that the ratios are nice, simple ones. And if we now play, for example, the 3 and the 4, and then we get exactly what we had before, a musical interval of the 4th, or the 4 and the 5, a third. And any two of them that you play give you a nice musical sound. Thank you. So the question is this the only one? Are there a lot of such musical triangles? And the answer is yes, there are a lot. And a Greek mathematician named Diophantus, in fact, wrote in a book called Arithmetica a system of finding all such triangles. That is the book that Fermat was reading when he made his famous conjecture, and that's what the next speaker will tell you about. Thank you.
The square of the hypotenuse of a right triangle is equal to the sum of the squares of the two adjacent sides. You'd not tolerate letting your participle dangle, so please affect the self-same respect for your geometric slides. Old Einstein said it when he was getting nowhere. Give him credit, he was heard to declare, Eureka, the square of the hypotenuse of a right triangle is equal to the sum of the squares of the two adjacent sides. Sure as shooting, when problems get in your hair, be like Newton, who was heard to declare, Eureka, the square of the hypotenuse of a right triangle is equal to the sum of the squares of the two adjacent sides. Now the two Wright brothers, before they conquered the air, like those others, Orville hollered, look here, the square of the hypotenuse of a right triangle is equal to the sum of the squares of the two adjacent sides. Thank you.
That wonderful performance was by Maurice Bobrow, who is a writer, composer, lyricist of numerous musicals and revues, as well as special entertainment for major corporations. Our next speaker is Lenore Blum, and she is the other deputy director at MSRI. She founded the Mills College Math and Computer Science Department, serving as its head or co-head for 13 years. Her talk is going to be about the history of efforts to prove Fermat's theorem, and she will also talk briefly about computer efforts to resolve the theorem by brute force. Lenore?
Well, that's some act to follow. And also, it's amazing to see all these people here out for mathematics. Andrew Wiles places the initial birth of modern number theory around 1630 when a French law student, Pierre de Fermat, received a copy of a translation from Greek into Latin of Diophantus's book Arithmetica. It was widely thought that Diophantus wrote his study of numbers around 250 AD. A typical problem taken from Book 2 would be to divide a given square into two squares, and Bob talked about that problem. By the late 1630s, Fermat's correspondence makes it clear that he absorbed Diophantus' ideas and that he had a number of creative ideas and results going well beyond Diophantus. My job this evening is to explain the meaning and context of one particular statement that Fermat wrote in the margin of his copy of Diophantus. Fermat certainly was not writing for posterity, but his annotations come down to us from an edition of Diophantus published by his son, his oldest son, after Fermat's death. By this curious route, a casual statement by Fermat has led to an enormous amount of mathematics, including the recent excitement of Wiles' proof. I'd like to describe the context of this statement by starting with Fermat as a person. Fermat was born in 1601 and studied law. In 1631, he was appointed judge in the French town of Toulouse. He held this position for his entire life. Fermat had an excellent classical education and was talented in languages, and in fact, he wrote poetry in a number of different languages. He was certainly part of the scientific and mathematical ferment of the time and worked on many areas of mathematics. And indeed, Newton later remarked that he was led directly to the differential calculus by Fermat's method of tangents. To put this a little in the historical time frame, the early 1600s was the time the Pilgrims were settling in America. Most of Fermat's scientific and mathematical ideas must be inferred from his correspondence. In modern parlance, he had serious writer's block. Although the question of publishing his ideas, especially in number theory, recurs in his correspondence, he essentially never published anything. I don't know about tenure for this guy. In addition, Fermat traveled very little, probably never even leaving southwest France. With one or two possible exceptions, he never had face-to-face meeting with other mathematicians, which is quite remarkable. I mean, contrast that today with so many international meetings and places where mathematicians get together, like at the Math Science Research Institute in Berkeley or the Newton Institute in Cambridge, where Wiles recently announced his result. Fermat died in 1665, at which time Samuel, the oldest of 5 children, began work on the project of publishing his father's mathematical work. Fermat's most famous annotation, indeed surely the most famous marginal note in all history, is the following quote. But this is just a photocopy from an edition of the Diophantus published by Samuel. This is the quote more closely in Latin, and since I suspect that some of you may not have a classical education equal to Fermat, I'll be kind enough to give you an English translation. It is impossible to separate a cube into 2 cubes, or biquadratic into 2 biquadratics, or in general any power higher than the second into 2 powers of like degree. I have discovered a truly remarkable proof which this margin is too small to contain. Fermat didn't have the benefit of modern algebraic notation, but we do. So let's try to express the idea that a cube can't be written as a sum of 2 cubes. Well, what is a cube? Well, it's a number like 8. 2 times 2 times 2. That is a product of a number by itself 3 times. For instance, a cube number naturally measures the volume of a cube. It's not just a coincidence we call raising to the third exponent to the third power cubing. Okay? So there we have an algebraic statement, at least of the first thing. So Fermat's first assertion was that it was impossible to find three whole numbers a, b, and c such that a cubed, a times a times a, plus b cubed equals c cubed. And when we're talking about whole numbers, we mean positive numbers, 1, 2, 3, 4, not 0. Suppose we were trying to disprove or show this empirically. Well, we have some props here, and we could do some experiments, right? I have a collection of cubes, right? And so I might be able to take one cube and see if it balances the sum of two cubes. We have a scale here, and we have various cubes lined up. 1 inch by 1 inch by 1 inch. I can't see, I guess you can, so that's one volume. Well, we might imagine that the weight is proportional to volume, so that's how we would use a balance to sort of check things out. Then we have, I guess, a 2 by 2 by 2, which would be of weight 2 inches by 2 inches by 2 inches, so volume 8, and so forth. So let's see if we might just check out with some examples. So some of these look pretty heavy. So what I'm going to start with is one, we have a 6 here, right? 6 cubed, 6 times 6 times 6. So how much should that be? Do we have someone in the audience who's, that's 216, good. And then I'm going to take a 5 cubed, that's 5 times 5 times 5, 125, and that weighs up there. The sum is 341. And let's see, suppose we want to prove Fermat, so I take a 7. 7 times 7 times 7 is what? Almost, right? Let's see. 3, so we had the sum there was what? 341, and now 343. Let's see whether, whoops. Almost, but not quite. So if I was an experimental mathematician, at least I didn't find a counterexample yet. So it's close but not exact. And Fermat was saying that no matter how hard one tries, it would be impossible to find two cubes of whole number sides that balance another cube with a whole number side. And Fermat asserts more generally the impossibility holds for all larger exponents. This is the more general statement. And notice, to show that Fermat is wrong, all you have to do is find a single example of whole numbers a, b, and c, and n greater than 2 that satisfy this equation. Although many people have tried, no one has found a solution n bigger than 2, and now Andrew Wiles says that no one ever will. It's impossible to know what was going on in Fermat's mind. The only proof of Fermat that we know is the proof of his theorem n equals 4, and by an ingenious argument using a technique called infinite descent. It's sort of a technique by showing if you have one example, you can get a lower one, and a lower one, and a lower one. He showed that the equation a to the 4th plus b to the 4th equals c to the 4th is impossible in whole numbers. He refers to the cases n equals 3 and n equals 4 frequently in his subsequent correspondence, but never returns to the general case. More than 100 years later, the Swiss mathematician Euler, who spent much of his time in Russia, gave a proof of Fermat for n equals 3. Fermat's seemingly innocent remark has led to an enormous amount of mathematics, although number theory was regarded almost as a recreational endeavor in Fermat and Euler's time. By the early 1800s, the deep work of the German mathematician Carl Friedrich Gauss gave number theory respectability and importance that it retains to this day. By the middle of the century, Fermat's statement has become known as Fermat's last theorem because it was the last of Fermat's assertions that remained unsettled, not because it was the last one that he ever stated. Gauss, perhaps the greatest mathematician of all time, felt that the question had little importance in itself, but was instead the tip of an iceberg of a far larger mathematical domain. In 1860, the French Academy offered a prize for work on Fermat's last theorem, and this led to a flurry of activity that, again, has continued unabated to this day. Some of the first general work on Fermat's last theorem was done by Sophie Germain. Germain was the first to make progress for a large class of n's at once. So up to this time, it had only been shown for particular numbers, in particular 3 and 4, and Sophie starts looking at a more general, takes a more general approach. And to give a sense of what it was like to be a woman interested in mathematics at the time, it is perhaps worth taking a few minutes to tell a little bit about this remarkable woman, so I'll digress for a minute or two. Sophie Germain was born in Paris in 1776, the year of American independence, and was a young girl during the French Revolution. For protection, she was kept at home. Starved for mental stimulation, young Sophie began to read math books in the family library, and this became a passion with her. Her family vehemently disapproved of such studious tendencies and, concerned for her mental well-being, took desperate measures. They denied her light and heat for her bedroom in order to force her to sleep at night instead of to study. But after Sophie's parents were asleep, she would wrap herself up in quilts, take out a store of hidden candles, and work all night. After finding her asleep at the desk in the morning with ink frozen and calculations on her slate, her family finally relented. By the time Sophie Germain was 18, Paris was settling back to normal, and the École Polytechnique was founded. Although women were not accepted, Sophie Germain collected lecture notes of various professors and started communicating with mathematicians using the pen name Monsieur Leblanc, so they would take her seriously. In 1804, after reading Gauss's Disquisitiones, Monsieur Leblanc began a lengthy correspondence with Gauss. It was not until 1807 that Gauss discovered her true identity. He remarked that the question of gender mattered little to him, and let me read to you a few lines from his letter to her at that time. But how to describe to you my admiration and astonishment at seeing my esteemed correspondent, Monsieur Leblanc, metamorphose himself into this illustrious personage who gives such a brilliant example of what I would find difficult to believe. Apparently she had sent him a theorem. A taste for the abstract science in general, and above all, the mysteries of numbers, is excessively rare. It is not a subject which strikes everyone. But when a person of the sex which, according to our customs and prejudices, must encounter infinitely more difficulties than men to familiarize herself with these sorting researches, succeeds nevertheless in surmounting these obstacles, then without doubt she must have the noblest courage. There was much progress over the years in proving Fermat. I'll put up a table here. Let me mention, and so we could see the progress progressing. We see the French Academy, Sophie Germain, and other things. But let me mention the flurry of excitement in the spring of 1847. Cautionary note. On March 1st, Lemay announced to the Paris Academy that he could solve Fermat's last theorem for all n by introducing complex numbers to the problem. Lemay enthusiastically told the Academy that he could not claim entire credit for this idea, since the mathematician Liouville had casually suggested the idea some months before. Immediately, Liouville rose to the floor saying he didn't share Lemay's enthusiasm and declined any credit for himself. Indeed, he suggested any competent mathematician approaching the problem for the first time would have thought of that idea. So what? But then the eminent mathematician Cauchy took the floor, indicating he believed Lemay would succeed, pointing out that he himself had presented to the Academy the previous fall an idea which he believed would lead to a resolution. But unfortunately, he said, he had not found time to develop his idea further. On March 22nd, both Lemay and Cauchy deposited secret packets with the Academy. This was a convention which enabled one to claim priority of ideas without having to reveal them. In the following weeks, they each published as notices in the Proceedings of the Academy, notices which, according to some of the books, were annoyingly vague. On May 24th, a letter from the German mathematician Kummer was read to the Academy's proceedings, pointing out how their proofs had failed. But Kummer added by introducing a new kind of complex number, an ideal complex number. So you get the dynamics of how these mathematicians work here. But indeed, Kummer did develop an entirely new approach, laying the foundation for what is now called algebraic number theory. In particular, he proved the theorem is true if n is a so-called regular prime. And he established a vastly more efficient way to verify the theorem for individual primes. Those were techniques that were used in this century. So moving ahead to the 20th century, Van de Ver, together with graduate students and desk calculators at the University of Texas, and that's in the 30s, used Kummer's idea to verify Fermat's last theorem for n less than 600. And then there was the advent of computers, and here at Berkeley, Derek Lamer, a longtime professor at Berkeley, was one of the first to use computers to work on mathematics. And in this way, he was able to confirm Fermat all the way up to n equals 4,000. And more recently, using a network of computers, Joe Buehler, who is in our audience somewhere here, verified that Fermat's last theorem was true up to n equals 4 million. So we're getting way up there. And in fact, if you think of it, if you try to get a counterexample over 4 million, even to show it was a counterexample, doing the computations would be quite difficult. So one might imagine a computer proof that could prove Fermat. It's not impossible to imagine that. But the techniques that were used just prove it for one n at a time. That methods that have been used could never be used to verify the whole theorem all at once. But now, just 5 weeks ago to the day, in one fell swoop, using mathematics and not computers at all, Andrew Wiles has proved Fermat's last theorem is true for all n. Thank you.
There's a delta for every epsilon. It's a fact you can always count upon. There's a delta for every epsilon. And now and again, there's also an n. But one condition I must give. The epsilon must be positive. A lonely life all the others live. In no theorem, a delta for them. How sad, how cruel, how tragic, how pitiful, and other adjectives I might mention. The matter merits our attention. If an epsilon is a hero, just because it is greater than 0, it must be mighty discouraging to lie to the left of the origin. This rank discrimination is not for us. We must fight for an enlightened calculus, where epsilons all, both minus and plus, have deltas to call their own.
Our next speaker is Professor Carl Rubin, who is a professor at Ohio State University, and he's visiting MSRI right now. Carl was also a PhD student under Andrew Wiles and has done some important work of his own in the theory of elliptic curves. And we're getting in now to the sort of meat of how Wiles accomplished this feat. And one of the essential ideas, a mathematical development that has its own history and was not considered to be linked in any way to Fermat's conjecture, but a very important part of number theory nonetheless, is the theory of elliptic curves. And you have to get a little piece of this in order to really understand the large-scale architecture of how this theorem was proved. So, Professor Rubin on elliptic curves.
Okay, well, let's start with an example of an elliptic curve. Here we have the equation y squared equals x cubed minus x. And then we have the graph of this equation. So we have the horizontal x-axis, the vertical y-axis, and on these axes we plot all the pairs x, y that satisfy this equation. Y squared equals x cubed minus x. And you get this curve with those two pieces. You are probably familiar with graphing equations. If you start with a very simple equation that has x's and y's, but no higher powers, then you get a straight line. If you have x squareds and y squareds, and maybe xy, but no higher powers than that, then you get what are called conic sections. You can get parabolas or circles. If you make it just a little bit more complicated, as we did here, by adding an x cubed, this is an elliptic curve. It's a little bit more complicated. It makes it a little bit more mysterious and a little bit more interesting. This particular elliptic curve was studied by Fermat. You've already heard about how he was reading in his copy of Diophantus, where there are lots of results stated about right triangles. Fermat had asked himself, are there any right triangles whose sides are whole numbers and for which the area is a perfect square? Simple question about right triangles. Fermat was able to prove that the answer is no. There's no such triangle. And he proved that by showing that this equation has no solutions with fractions x and y except for the 3 points up there, where y is 0 and x is either -1 or 0 or +1. So elliptic curves, which are going to play an important role in the proof of Fermat's last theorem, their study was really begun by Fermat. And we know all of this, and we know he was able to prove this because he did manage to put the proof into the margin of his Diophantus. So this is one elliptic curve, but there are lots more. So if you take any two different integers, non-zero integers, so two different positive or negative whole numbers, call them a and b, look at the equation y squared equals x times x minus a times x minus b, that's an elliptic curve. If you take a to be 1 and b to be -1 and multiply out that product, you get y squared equals x cubed minus x, the example we were just looking at. There are two types of questions mathematicians would ask about elliptic curves. One of them is, like Fermat asked, if you've got an elliptic curve, how can you find all the solutions? Maybe you want to find all the solutions where x and y are whole numbers, or maybe where they're rational numbers like Fermat did. On the other hand, you can ask questions about the whole collection, the whole family of different elliptic curves, by trying to identify important properties of elliptic curves. And this second problem can help you with the first, because identifying the right sort of properties can help you in this question of finding solutions. There's one particular property of elliptic curves that plays a crucial role in Wiles' proof of Fermat's last theorem, and that's what we want to talk about now. This is the property of an elliptic curve called being modular, and I'd like to explain what that means. When mathematicians have a question which may be too difficult to answer, one strategy is to try to replace it with a simpler question, or maybe a whole lot of simpler questions. In this case, we start with the question, how do you find all solutions to y squared equals x cubed minus x, or the same thing, all x and y for which y squared minus x cubed minus x is 0? That's the hard question. The easier question is, take a number like 5 and ask, how often is y squared minus x cubed minus x a multiple of 5? Well, that's a question you can answer with just some arithmetic. Here we have a table of the values of x going from 0 to 4, the values of y going from 0 to 4, and then in the table we just write down the value of y squared minus x cubed minus x. You notice a couple of zeros. Those correspond to actual solutions, where that difference is 0. But there are also some numbers that are divisible by 5, but not 0. Those are the ones that are sort of answering our question now. Let's mark them. There's 7 in this picture. Now you might ask, why did I stop at 4 for x and y? Why didn't I continue? Well, I leave it to you to check that if I were to continue x or continue y, the pattern of which numbers are multiples of 5 would just repeat. The numbers themselves would change, but this pattern of the 7 numbers which are divisible by 5 would remain the same. Well, there's nothing special about 5. You can do this for any number. We'll be interested in prime numbers like 2, 3, 5, 7, and so on that have no divisors except for 1 in themselves. Take one of these prime numbers, call it p. make the same sort of table, count the number of values that are multiples of p, and call that number n sub p. This table we made for 5 shows that n sub 5 has the value 7. Well, you can compute this for the other primes. Here's a table for some of them. I've listed the primes up to 31, and then I've listed a few larger primes. If you start to look at this table, you'll notice some patterns. One thing you might notice is that often, but not always, the number in the top row is the same as the number in the bottom row. Also, if you look at it for a while, you'll see that after the first one, after the number 2, all the numbers in the bottom row are 1 less than a multiple of 4. What do these patterns mean? Well, it turns out there's even more structure to these numbers than you might guess. In 1814, the mathematician Carl Friedrich Gauss, who's considered one of the most eminent mathematicians of all time, found a formula, a recipe for computing this number n sub p. The recipe goes like this. 2 is always a little separate, so you just keep it separate and you count that n sub 2 is equal to 2. Otherwise, you look at your prime. If it's 1 less than a multiple of 4, then the number n sub p for that prime is just the number itself. And if it's 1 more than a multiple of 4, there's a slightly more complicated formula. But if you look at this table here, I promise you that I computed the numbers in the bottom table by using Gauss's formula, and that's a lot easier than writing out all the values of x up to 1,000,000 and all the values of y up to 1,000,000 and filling in the table. Well, what Gauss's formula tells us is that this sequence of numbers, n sub 2, n sub 3, n sub 5, and so on, has a very special structure. And because of this special structure, we say that this elliptic curve, y squared equals x cubed minus x, is modular. Well, you can do the same thing with any elliptic curve. Remember, we have a whole family of elliptic curves. What that means is you start with your equation. You can build a sequence like this in exactly the same way by making a table, counting the number of divisibilities you find. So you get a sequence, n sub 2, n sub 3, and so on. And we define this elliptic curve to be modular. We say it has the modular property if the sequence you get this way has the special kind of structure analogous to the structure that Gauss's formula gave for the elliptic curve y squared equals x cubed minus x. So to be modular is a special property of elliptic curves which is related to this sequence you get from the elliptic curve. Well, for a sequence like this to have this modular property is really very special. Very few sequences, if you just wrote down a sequence, would have this property. We know that the sequence coming from y squared equals x cubed minus x has this property. But it was very surprising when in 1955, the Japanese mathematician Yutaka Taniyama suggested that maybe all elliptic curves are modular. He suggested this to a group of his colleagues at a mathematics conference in Japan, but no one really knew what to make of this suggestion because no one really knew a reason why this should be true. So the suggestion didn't get a lot of people interested for a while. Taniyama died in 1958, but sometime after that, a colleague of his, Goro Shimura, who's now a professor at Princeton, looked into this some more. He thought about what Taniyama had suggested. He made this conjecture more precise and also made it more believable. He came up with some reasons why you might expect it to be true. So mathematicians call this a conjecture, meaning it's a guess. It's something they believe to be true, but don't know how to prove. This conjecture, over the years, gained more and more support in the sense that lots of people believed it. Until the last few years, certainly, it was universally believed by mathematicians, but still no one had any idea how to prove it. Well, it's this conjecture that every elliptic curve is modular, which goes on to play a crucial role in the proof of Fermat's last theorem.
Our next speaker is Ken Ribbett. And Ken is a professor at Berkeley, right across the bay. His specialties are number theory and arithmetic algebraic geometry, which is a difficult field. Ken Ribbitt's own research has played an important part in the pieces that come together and establish Fermat's last theorem. And so he's going to talk about how all these pieces fit together, including his piece, and tell us a little bit about what it was like to be there on June 23rd in Cambridge when the theorem was announced. Ken Ribbitt.
Thanks very much. I would like to take you from Yutaka Taniyama in 1955 through June 23rd of this year, possibly a little bit beyond. If one asked 20 years ago, or even as recently as 1981, what Taniyama's conjecture had to do with Fermat's last theorem, the answer would have been nothing. There's a man who's very important in the story. His name is Gerhard Frey. He's a mathematician in Essen who really saw that there was a connection for the first time. Frey was in Seattle last week, and I'd hoped to bring him here. Unfortunately, he's back in Europe. I don't even have a photo of him to show you. What I do have to show you is a letter that he wrote me in 1981, where he proposed coming to Berkeley for 2 months to talk about modular elliptic curves and modular curves and Fermat's last theorem. I was very busy at the time. I thought maybe I would discourage him from coming, but in fact he was welcomed with open arms in Berkeley, and we had many discussions about elliptic curves. And he wrote down quite a bit in the way of formulas linking elliptic curves and Fermat's last theorem. And frankly, neither of us really saw what he was up to. He had the connection between elliptic curves and Fermat's last theorem, but he didn't see how to relate Taniyama's conjecture to this important assertion of Fermat. Now, if we jump a little further, we see that in 1985, the situation had changed drastically. Frey announced to the mathematical public, in fact, a very small group of mathematicians, that indeed Taniyama's conjecture had as a consequence Fermat's last theorem. And this was the first time that anyone had really succeeded in linking up Fermat's last theorem with the tools of modern mathematics. The success, unfortunately, wasn't complete, because Frey gave his lecture in a little retreat in Oberwolfach in the Black Forest. There were about 20 people present. I certainly wasn't among them. And the vast majority of the 20 people realized by the end of the lecture that there was a big mistake in what Frey was saying. The mistake occurs in his manuscript, which was only 2.5 pages long. It's a little bit out of focus for you, but in fact, that's the way most mathematicians saw it. There was a very important idea in the manuscript, the link between the two, but it really wasn't made complete. A lot of the people who were present in the Black Forest, this was January 1985, came rushing back to Paris and tried to deepen the link that Frey had first seen. And there were a number of people who had ideas that made some partial progress in the direction of really setting up what Frey had hoped for. I was busy teaching calculus in Paris and was hoping that people would get somewhere, but it didn't really seem clear how the result was going to come out. But again, by the summer of that year, the situation had changed. There was a mathematician in Paris named Jean-Pierre Serre, who's certainly one of the greatest living mathematicians. He won the Fields Medal, which is our version of the Nobel Prize. Serre, writing from his mountain home in August during the vacation, realized that there was a precise method of linking up Fermat's last theorem and Taniyama's conjecture. Unfortunately, this introduced a new layer of complication, because in his letter, which he actually wrote to a young colleague in Paris, Jean-François Mestre, he explained that one couldn't directly make the link that Frey had started, but instead what would happen is that you could only prove 2 little conjectures, and if these new conjectures of Serre were established, then you would know that Taniyama's conjecture implied Fermat's last theorem. Now, the news of such things spreads very rapidly among professional mathematicians. This was the case because as Mestre was getting this letter, he was boarding a plane for California, and he came to a workshop which we had at Humboldt State University in Arcata, where once again there were something like 60 mathematicians assembled. And this caused quite a line at the coin-operated photocopy machine, because everybody was very eager to get news of this deepened link that Serre had set up. Now, one thing I should point out is that this indicates, at least it seems to me, illustrative of the way mathematicians work. During the year, we're busy teaching courses, and we don't really have time to interact with one another. And it's been the pattern that we've had week-long conferences, typically when universities are out on vacation, so we can live in the dormitories and enjoy dormitory food. And we typically have 4 or 5 lectures a day, which are surrounded by walks in the forest and discussions amongst ourselves. And this is a very intense period for people who are unable to see their colleagues during the academic year. Electronic mail has changed that to some extent because now we can bounce news around the world, but it's still very important to speak to people face to face and to see exactly what the other person has done. Now, for roughly 1 year, Serre's conjectures, which he called C1 and C2 in the letter, were unsettled, and the person who actually was able to prove them is myself. Yours truly. I proved the conjecture in 1986, and the way it happened is that at the time when I was proving this conjecture, there was an International Congress of Mathematicians. There's one every 4 years. The next one will be next summer in Zurich, and it happened to be in Berkeley, California. So there I was sitting with Barry Mazur, who's a professor at Harvard. We were having cappuccinos on the south side, and we were talking about these conjectures C1 and C2, and I told Barry that I had more or less proved them, but that I still didn't understand to what extent my techniques would work. And Barry was the person who said, well, you're just being silly, because in fact what you're doing is proving these conjectures directly. And by the time I had licked off the foam from my cup, I realized that in fact he was absolutely right. And since there were 2,000 mathematicians present in Berkeley, I was able to confide in a few of them that this was going to work, and then the news just spread. And it was somewhat embarrassing because there was a lot of interest in Fermat, much more than we realized at the time, and people were really pressing me for the details of the proof, which were still being washed off the cappuccino cup. And what happened is that, again, by coincidence, there was a special year at MSRI, which is this Mathematical Sciences Research Institute. It's now sometimes called Emissary because it reaches out and tries to convey mathematics outside of professional mathematicians. And I gave a lecture, 1 lecture a week, for a period of several months at the MSRI to specialists in my field. And this was absolutely great because as the proof was taking shape, I got a lot of direct criticism from people who really knew all the ins and outs of the mathematical objects that I was working with. And by the end of that special year, I had an airtight manuscript. At least I thought it was airtight. But I do want to point out that the process of publishing a proof is a very lengthy one because there are referees that intervene and make changes that the author may or may not agree with, but nevertheless, there's some negotiation which takes place. You get a final manuscript, it goes to the printer, and then there's this concept of a publication delay before it comes out on your local newsstand. And so actually 4 years elapsed between the time when I realized that I was going to prove this and the time that it was actually in print. Well, that's the sort of main thing that happened before 1993, but then the next chapter of the story starts. So this is Andrew Wiles in a photograph that I took of him quite a number of years ago. Perhaps it's a photograph from 1980. I first met Andrew in 1975 when he was a research student in Cambridge. His advisor, John Coates, is a very close friend of mine, and he was busily solving all the problems that Coates was putting to him. We certainly became friends and colleagues, especially since Andrew has done most of his career in the United States. After his thesis, he became a postdoc at Harvard, and after his 3 years at Harvard, he stayed on as a permanent professor in Princeton, New Jersey. I have some other photos to show you. I don't know how easy this is to see, but this is some variant of the published photo of Andrew writing down the theorem that he can prove Taniyama's conjecture for the class of elliptic curves that intervene in the story. You might have read in the newspaper accounts that many of the mathematicians were taking both notes and photographs during this lecture because we sort of well understood what was going to happen. And now in the next photograph, you see 2 gentlemen who may be familiar to you. The person on the right is the previous speaker, Carl Rubin, and I got myself in the center, and that's Andrew. He's finishing what turned out to be Napa Valley Brute. For some reason, it found its way to Cambridge, England on June 23rd. One thing that I think was absolutely amazing is that when I went through my Wiles file trying to find evidence of his interest in Fermat's last theorem, I found a postcard that he mailed me, I believe, in 1980, in which he talks about my demonstration of Fermat's last theorem. This was his way of making a joke, but I think it was very much on his mind. He explained to British television on June 24th that he had been thinking of Fermat's last theorem ever since he first encountered it as a statement when he was a boy. And when he learned that Fermat and Taniyama were connected in 1986, he basically closeted himself. He actually worked in an attic for 7 years trying to get a proof of Taniyama's conjecture. And this is really an unparalleled event in the history of mathematics that I know, because usually people work in close contact with their colleagues. They go to conferences and they talk, and Wiles thought this was so important that he really had to work alone until he knew that he could solve the problem. Next, I just want to tell you, of course, that Andrew announced that he had solved Taniyama's conjecture. I guess you know that by now. And one thing that I want to stress is that there's a tremendous amount of modern mathematics that goes into his proof. You might have gotten the impression from preliminary accounts that he had somehow sat down and written 200 pages, which were independent of all the developments that you've heard about tonight. But in fact, what he did was he took everything that he needed from the most potent techniques in modern number theory, including many that really hadn't been devised when he started working the problem in 1986. I'd just like to tell you who the personalities are involved, just so you get some sense of the global sweep. Haruzo Hida is a professor at UCLA, but of course he's from Japan. He's from Sapporo, where a lot of the ideas linking modular forms and elliptic curves first began. Barry Mazur I've mentioned before. And then there's a topic called Iwasawa theory, Yukichi Iwasawa, who was a close colleague of Shimura. And of the people whose work that was used by Andrew Wiles, of course, Carl Rubin, whom you've just heard from, and Ralph Greenberg, who's a professor at the University of Washington in Seattle. And then there's something called Euler systems. Euler is the person who first solved Fermat's last theorem for exponent 3. And Euler's name occurs in many different places in number theory. And there's a man named Viktor Kolybagin, who's from Moscow, who found a new technique in the theory of elliptic curves. And he named it Euler systems because he thought that that was very appropriate in the context in which he worked. And it was really Wiles, for the first time, working with some ideas of Matthias Flach, who was another student of John Coates in Cambridge, who really bent the Euler systems into the context that was needed. My name also occurs in the paper because I proved something involving congruences between modular forms. These come up in the proof. And then there's another aspect involving modular forms, which really relies on work of Robert Langlands, who's a professor at the Institute for Advanced Study in Princeton, and Gerald Tunnell, who's a professor at Rutgers University, also in New Jersey. Well, what I'd like to do for you next is just summarize the logic, the way the proof goes if you have at your disposal the tools that have surfaced since 1985. If you want to prove Fermat's last theorem, you do it by contradiction. You suppose it's false, and that means that there really are integers a, b, and c, with a to the n plus b to the n equal to a perfect nth power. Of course, n is some number which is big, bigger than 4 million. You know that when you start because of the computer calculations. I think you just use that it's bigger than 5. So you start with this counterexample, and you do this important thing that Fry wrote down. You make the elliptic curve, y squared equals x, and so on. This is just some variant of the elliptic curve that Carl Rubin told you about. Now it's a little more complicated, and Gauss doesn't tell you that it satisfies Taniyama's conjecture. But Andrew Wiles does. That's what we learned on June 23rd, that this elliptic curve satisfies Taniyama's conjecture. On the other hand, if you believe what I told people in 1986, you know that it doesn't. So it's an impossible situation. You have an elliptic curve which has contradictory properties, and the only thing that makes this elliptic curve is the supposed solution of Fermat's last theorem. What's wrong? There wasn't a solution. And that's the way the proof ends. Now, you can look at this from another point of view. You can just have the chain of ideas in terms of when they occurred. Taniyama made his conjecture in 1955. Of course, before that, we could have put Fermat in 1637, one says, but there's a lot of intervening mathematics, and it didn't fit into the margin of the slide. So we just jump ahead to 1955, and then we have Taniyama in 1980. Excuse me, we have Fry's ideas in 1985, which were fully realized only in 1986. And then there's a big jump of 7 years before Andrew's lecture in 1993. Well, in conclusion, I'd like to say that this proof of Fermat's last theorem is a tremendous triumph for modern mathematics. It's a tremendous triumph for number theory. Of course, it's a wonderful personal triumph for Andrew Wiles, and I'm very happy to have been part of it, and it's a pleasure to be here tonight to tell you about it.
Our next speaker is John Conway, professor of mathematics at Princeton. And Ken Ribbett told you a little bit what it was like to be with Andrew Wiles, and John tells me he's going to tell us a little bit about what it was like to not be there. Now that's because John Conway is one of Andrew Wiles' closest friends and co-workers, and they are in fact working on a book together. And John Conway was probably the first person outside of Cambridge to hear about it via email. He's also the inventor of the game of life, which you may have heard about if you're a computer science person. And after John's talk, there'll be a break, 15 minutes, 10 minutes or so, and then we'll come back for a panel discussion. So here is John Conway with his personal history of Fermat's last theorem.
Well, you know, one of the first things I want to say is that I'm not really connected with this at all, and you'll see why that's true later. But I was very interested. I think among the people here, I'm probably the person who's known Andrew Wiles for the longest time. And I'm very, very delighted, of course, that he succeeded. But I'm going to give you a very quick history. I'm going to go right back to 3,600 years ago, because, you know, it's really very interesting to me. I'm very interested in mathematical history. This problem really does have a history that far back. This clay tablet actually contains essentially a formula. It's the formula in Diophantus's book that gives you integer solutions of x squared plus y squared equals z squared. And then it plugs various numbers in and gets particular solutions out. That's 3,600 years ago. Another thing that sort of dates from roughly the same time is another Babylonian clay tablet. This one you can actually read if you like. If you know that a sort of V-shaped symbol means 1 and a V-shaped symbol on its side means 10, you can actually read this. It means there's 1 part and then 24 parts of the next degree down, which differs by a factor of 60 and so on. And you work it out. What this is telling you is that the length of the side of this thing is this particular number 1.4142, etc., which is very, very close to root 2. So that tells us people were interested in this 1, 1, root 2 triangle 3,600 years ago. By the way, these dates are not at all exact. I mean, it might have been 3,601 years ago. But it could easily be several hundred years out. Nobody knows exactly when Diophantus lived. He could have lived in the 2nd, 3rd, or 4th century AD. Supposing he lived in the 2nd, then it's about half the time ago, 1,800 years ago, that he wrote his book, which proves that that Babylonian formula gives all the solutions to the square problem. I'll put on very quickly that 392 years ago, Pierre de Fermat was born. And he's really the greatest number theorist after Diophantus, and a very great number theorist in all time. 356 years ago, roughly, we don't exactly know. Well, Bachet's edition of Diophantus, a new translation of Diophantus, appeared a few years previously, and Fermat writes that famous marginal note. Now, you know, you've heard the history of Fermat's last theorem, very well expounded by Lenore Blum and a few other things by other people here. So I'm going to omit the Fermat problem itself here, the last theorem, but, you know, it's only one of many theorems that he enunciated, both as marginal notes in his Diophantus, which were later published by his son, and also in letters to other people. And these other theorems lasted quite a respectable time. 1749, Euler proved Fermat's theorem that tells you when a prime number is the sum of 2 squares. The answer is if it leaves the remainder 1 when you divide it by 4, it is. If it leaves the remainder -1, it isn't, or 3. Fermat asserted that every integer was a sum of either 3 triangular numbers, I'm not going to stop and tell you what that means, or 4 square numbers, or 5 pentagonal numbers, and so on. Well, the 4 square case was proved first by Lagrange in 1772. The 3 triangles was one of the things published by Gauss in 1801. He actually found it a year or two earlier. Cauchy, who's also been mentioned, proved the 5 pentagons theorem and all the others. And there are other theorems, I'm not going to mention them in detail. The last few of them, I believe, apart from the last one, was proved by Jacobi in the 1840s. So you see, they lasted 200 years, okay? The last one lasted 350 years. Well, big deal. I'm jumping to 10 years ago now, roughly. And these dates are just about as inexact as my previous ones, by the way, maybe 12. Faltings, now at Princeton, but that was what got him his job at Princeton and the Fields Medal, proved the Mordell conjecture. I won't tell you what that is exactly, but it does follow that for any particular n, there are only finitely many really different solutions of the Fermat problem. So you can't have more than a finite number. There probably aren't any. In fact, we know now that there aren't. But Mordell's conjecture entails that there couldn't be infinitely many for any given n. 8 years ago, Andrew told me he started working. He seriously started working a lot harder 7 years ago after Ken Ribert proved the theorem you've heard him talking about. Jump now to 6 months ago, when Wiles tells 2 colleagues in Princeton, you know, I'm an emissary to MSRI from Princeton, really. One of the things I'm trying to do is point out there are a few Princeton names as well as Berkeley names here. Well, Peter Sarnak told me that one day in January, Wiles turned up and late at night and said, I've got something to tell you. And he then made him sit down and told him. And then he worked with Nicholas Katz, the other person he told at the same time. He actually announced a lecture course. Only Katz knew that it was going to prove Fermat's last theorem at the end of it. So the audience rapidly shrank to one person, Katz. And they worked through, and there was a difficulty. Perhaps I should mention that. There was a portion that Andrew didn't feel terribly secure about. He wasn't entirely familiar himself with the concepts. That's why he got Katz to help out. And there was a difficulty. And 12 weeks ago, in the middle of May, he found what he calls the 10-minute argument that solved that difficulty. And I don't know whether he calls the 10-minute argument because he found it in 10 minutes, but he told me it took him only 10 minutes to explain it to Katz, where he'd been working for several months on this very point before then. Now, this is the first time I come in. 6 weeks ago, I heard about the proof at a party in Princeton. And then I asked all my friends in Cambridge to tell me what went on at Wiles's talks. Well, you heard, 5 weeks ago to this day, he announced the proof. His lecture, his third lecture, was to start at 10 and end at 11. That's 11 a.m. British time. That's 6 a.m. in Princeton time. And indeed, I heard it shortly before 6. He must have finished early. I heard it at 5:53 a.m. in Princeton. I couldn't sleep. So that's 5 weeks ago. 4 weeks ago, Wiles came back to Princeton, and there was a lovely party. We had, instead of tea at 3 p.m. in the math department, we had champagne. It's the main difference. And also the president of university, for some reason, turned up to the mathematics department too. And I was talking to him, and I said, where is Andrew? It was about 5 minutes after tea time was officially due to start, and then suddenly everybody started clapping. I still couldn't see him, but then he walked in. It was a very nice, touching moment, because he walked in, and he was leading one little girl by the hand and holding his other little girl in his arms, and they were a little bit frightened by the cameras that were flashing and everything, but a very, very nice moment. He said a few words. Well, now past 3 weeks ago, this Fermat Fest is planned. 20 hours ago, I arrived in San Francisco. Well, rather more than 1 hour ago, since we're running late, this Fermat Fest started. About 10 minutes ago, I hope, I started talking, and now I'm stopping.
We're going to take an intermission now. Please come back. We've got a panel discussion that'll be starting. And if you have questions, find one of the cards out in the lobby and bring it to the side of the stage there, and we'll include those questions in the panel discussion. Thank you. We're going to have kind of a panel discussion now, get at some of the implications and take some questions. You've met all the panelists so far except for Lee Dembart. Lee is a journalist and science writer and book reviewer. He's been a reporter for the New York Times, Wall Street Journal, LA Times, San Francisco Examiner as well, and he's also an attorney. And you've met the other speakers. So, Lee, maybe we should start with you since you haven't made a presentation. Outside of mathematics, what is the significance of this? Why should people care who are not mathematicians about this kind of work? How would you explain it to other people?
Well, if your question is, what's the good of this, as a lot of people have asked me in recent weeks, my only answer would be, gee, that's like asking, what's the good of the Sistine Chapel? What's the good of Beethoven's Ninth? These are great achievements of the human mind, which we can all revel in and enjoy for their sheer beauty. Think of what we have heard here tonight. This is a problem whose origins go back into antiquity, many thousands of years ago. It's a problem that lots of people have thought hard about, the specific problem, for 350 years, and we now know it's true. Furthermore, Fermat's last theorem itself has the property that it's accessible, unlike much of what mathematicians do and talk about and think about. The Riemann hypothesis, which is still outstanding, would be very hard, I understand. I don't understand it, and it would be very hard, I understand, to explain to non-mathematicians what it is. But Fermat's last theorem can be explained, and we've heard it explained tonight, at least what the statement is. And so this is an opportunity for non-mathematicians to understand, to get a glimpse into the great beauty, the sheer beauty of mathematics and what mathematicians do and how they think about it, and this great intellectual structure that has been being developed since, formally since the time of the Greeks, and that continues to be developed today. Is it a cure for cancer? Obviously not, but there are much more things in the firmament of human endeavor than cures for cancer, and this is one of the great ones.
Do the mathematicians agree basically with that being the right way to tell the world why you're excited?
There's this great thing, you know. You don't understand something until you've proved it. You know? And I feel this great desire to understand something. And surely that's, you know, a thing that we can appreciate in itself. Just we want to understand. We want to know what's going on. And now, a few people will be in the position of understanding why this particular thing is. Not too many.
Well, this question was asked by a lot of people, and this is one of many versions of it, but considering that it took 3 months to find the error and some other proofs, and many false proofs have been advanced, Lenore, why is there confidence that this proof is really going to hold up? How do you know that Fermat's theorem has been proved?
It's really interesting because, in fact, you hardly hear any doubt at all. And I think one of the things, and Ken can probably talk to this even more, is that this is being proved within a context of a program of the 20th century. I mean, there's a whole lot of structural mathematics there. It's almost true for structural reasons. The ideas are not coming out of left field at all. It's coming through a very direct pattern and program of mathematics. But on the other hand, there's a lot of vested interest in it, in the sense that because so many people are involved in so many parts, we don't have as many critical eyes. And there is I think that is something to be cautious of, but I think it's just very slight. I think there is a sense that this is really solid. Ken?
Yeah, I think the level of confidence in it just grows from day to day because people are really thinking about the major issues involved, and what they see is a proof where the major ideas are very clear. And if there's something wrong, well, there may be some problem with really justifying fully one of the steps, but then we have the feeling that we can come in and we can really shore that up because the thing structurally just makes sense.
more broadly, there is a serious problem in recent years, which has been in science in general, which has been described as publication by press conference, in which scientists announce their results or alleged results about one thing or another literally at a press conference and not in a refereed journal and so forth. The most egregious recent example is the cold fusion announcement of, I guess, 4 years ago now, which turned out to be complete nonsense. The press should be faulted in this regard because many newspapers and reporters and so forth simply cannot tell the difference and have no means of telling the difference between what's right and what's wrong. Somebody makes an announcement, you don't want to be scooped by the opposition, by the other papers, and so on and so forth. And it should be underlined. I don't mean to in any way to equate Wiles' proof of Fermat's last theorem with cold fusion, but it should be underlined that every line of this proof has not yet been checked.
That's perfectly true. And of course, there could be a mistake in that. There's a very definite difference between this and some other things, you know. The basic thing is, you ask, could you conceivably prove it this way? Would arguments of this type get there? And every now and then, there's a calculation involved. Could you calculate that thing? And if you did and got a certain answer, would it be right? So, I mean, this is what Ken was saying before, to some extent. The mathematicians in a position to know can see that a program like this might succeed. And, you know, then Andrew Wiles is a very careful, cautious, conservative person. That goes into the equation. Everything does. After all, we're humans. I mean, even Andrew Wiles is human. Even I'm human. And, you know, we can make mistakes, and he's made some. But you can see that it could be done like this. You know, with a recent flawed attempt to prove the theorem, Gert Walting's a great expert, said, if it could have been done like that, I would have done it. He knew straight away. This time, the experts right from the start are believing it. Why? Well, because they see it's part of an intellectual program that could succeed. And Wiles has good credentials, you know, etc. I mean, there are a whole lot of things. But, yes, there could be some things that need patching. Maybe there's something that can't be patched. Maybe there's a really serious hole in this proof. It's conceivable. But we have good reason here to believe that this is a pretty sound proof.
Now, we got this question a few times, too. Did Fermat really have a proof? And what is the general thinking? Is there something that perhaps has been missed all these years, or was Fermat just making an informal comment? What's the view of the professionals?
We talked about this earlier, actually. I think most people feel that Fermat did not have a proof. But on the other hand, John really believes the other way, I believe. You were trying to argue the
yes,
other fashion.
I've just been opening my mouth rather a lot, so I was hoping to have a chance to rest for a time. But since I'm on the underdog side here, yeah, I'm actually sort of perhaps 50-50. The general consensus among those in the know seems to be that Fermat probably deceived himself. But there are some difficulties with this point of view. First of all, he wasn't writing for anybody else. It was a note to himself. So there's no question of his reputation, as it were, being on the line at the moment that he wrote that marginal note. It's a memorandum to himself. It's possible that he just made a sign error. And, you know, so he possibly wrote that note only a minute after he found the proof, and there was a sign error. I think that's unlikely because he comes back several times, and he did produce a proof for n equals 4 later on. You have to answer this question if you believe he didn't have a proof. What did he think he had? What was the proof that deceived Fermat, that Fermat deceived himself with? It certainly wasn't these later proofs that do exist all over the place that use non-unique factorization, or sorry, use unique factorization when it doesn't exist in certain extended number fields. Those ideas weren't available to Fermat. It's a very interesting question, and I don't know the answer. We shouldn't take the fact that, I don't feel that we should take the fact that mathematicians haven't found one until now as sort of evidence that there wasn't one that was available to
Ken, you look like you're...
I'd like to amplify that and add that the fact that we know Andrew Wiles has a proof and that this wouldn't have been accessible to Fermat doesn't mean that Fermat didn't prove it. If he had a proof, it was certainly a different one.
I wouldn't be surprised democratized either way, so to speak, in this, really.
So there's still an open question here for anybody looking for for some work. What was Fermat's proof? It was not the proof of Andrew Wiles. What's the simpler proof?
Even if it was a fallacious proof, what was it? That would be a very interesting... That would be interesting.
There's a life's work for someone in the audience.
Remember that some of the other theorems of Fermat lasted for 200 years, and some of them have very simple proofs.
Interesting. Oh, you mean some of...
350 years is, you know, it's less than a factor of 2 bigger. It might seem quite a lot to you people, but...
Well, squaring the circle took 2,000 years.
Yes,
right?
yes.
This question was aimed at Ken Ribbett, but maybe everybody can have a... What is, if Fermat's theorem itself is not interesting, what is the significance of the Taniyama conjecture and the kind of, you know, people say that Wiles' work fits into the larger flow of mathematics. Talk about that larger flow. If Fermat was not an implication, would this still be exciting work that Wiles had done?
Well, it would certainly be exciting to professional mathematicians, but I think honestly we wouldn't be here tonight. There are many people who are fascinated by Fermat's last theorem, and I think among mathematicians some are and some aren't. Taniyama's conjecture is fascinating to me because it represents a connection between 2 different kinds of mathematics and 2 different kinds of objects. Namely, you have the elliptic curves given by simple algebraic equations, and then you have what Carl Rubin called recipes for finding numbers of solutions to these equations modulo 5 and other prime numbers. And these recipes, they fit into the theory of modular forms. Someone talked to me during the intermission about elliptic functions. This belongs to another branch of mathematics called analysis. And the fact that there is a connection between these 2 different branches is astonishing. And if we understood it better, I think we'd know really a lot more than we know today.
Here's a question in a different direction. Most of the speakers tonight have been men. And what is the picture for women in mathematics, and what is the audience seems to be a little more heterogeneous than the speakers. How is mathematics as a field, maybe at the risk of throwing the question to the wrong person, Lenore, would you want to get us started at least?
Well, I probably am the right person. There are many, many issues here. I mean, is mathematics a good field for women? That's a particular issue, and I would say absolutely, it's great. I mean, I hope that people here are starting to see the excitement of it. Working on mathematics is just wonderful. What about the situation for women in mathematics? I mentioned Sophie Germain and her experiences. Have things changed since the French Revolution, American independence? And there has been an interesting, poignant history of women in mathematics. A woman could not become a graduate student at Princeton University in mathematics until 1968. It was very, very recent. But the situation has changed a lot. In this century, at the turn of the century, and in the United States, before World War II, the situation for women in the United States was quite good. And that sort of lasted through the war effort, and women were very involved in mathematical and technical fields. There was, historically, after the war, some kind of effort to put women back in homes. And I think that affected women in many fields, including mathematics, when the numbers of women getting PhDs plummeted down to 6%. Now again, we're up to about 20, 25%. So there is a very significant number of young women going into mathematics today. Past 20 years, there have been many programs to encourage women in mathematics. I've been involved with quite a few. There's the Association for Women in Mathematics, which is a professional organization. Right here in the Bay Area, there's the Math Science Network. There are summer programs. There's the Mills College Summer Institute for undergraduate women. At MSRI, we've been, this year, as part of our emissary effort to be much more involved with social issues, we have been really paying attention to participation of women and minorities in mathematics.
People often say, you know, mathematicians do great work when they're young, but when they get to be 30, 40, they're over the hill. Does anybody agree or disagree?
Well, we're all over the hill.
Well, I mentioned
We're all over. Well, how old is Andrew Wiles?
40.
40.
Plus epsilon. That's important for the fields now.
So he's a counterexample to the burnout at 40.
Oh, I think there are a lot of counterexamples.
Yes.
But it is true that in mathematics, as in music, as in chess, there are child prodigies. And those, I think, are the only fields in which there are real child prodigies. You could not imagine, I mean, Mozart wrote great music when he was 8. You could not imagine somebody, an 8-year-old, writing a great novel. It's not that the 8-year-old couldn't have mastered the techniques of composition and so forth, but would not have the life experience to write a great novel.
It's less true now than it used to be, partly because to do really good work at the forefront of mathematics now, you just have to know such a lot, and it takes a long time to learn it. So that age, the age at which mathematicians are productive, is creeping upwards.
So could there ever be another Ramanujan, a person who comes from an untutored background but has such enormous talent that they can really participate? Or do you have to go through a standard academic career to really become a mathematician today?
I think this still goes. I mean, I think, you know, there are lots of different people in the world, and mathematicians are very different to each other. There's not a standard model for mathematicians, I don't think.
Well, here's the question. Is this a golden age of mathematics that we're in today?
Yes.
The only thing left to do is to thank our speakers and panelists for this evening.
Counting sheep when you're trying to sleep, being fair. When there's something to share, being neat. When you're folding a sheet, that's mathematics. When a ball bounces off of a wall, when you cook from a recipe book, when you know how much money you owe, that's mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt, oh, try as you may, you just can't get away from mathematics. Andrew Wiles gently smiles, does his thing, and voila, QED, we agree, and we all shout hurrah, as he confirms what Fermat jotted down in that margin, which could have used some enlarging. Tap your feet, keep in time to a beat of a song, while you're singing along, harmonize with the rest of the guys. Yes, try as you may, you just can't get away from mathematics.